Welcome to our exploration of Earth's magnetic field. Today, we are going to dive deep into the invisible shield that surrounds our planet, known as the magnetosphere, and understand how it interacts with the dynamic environment of space. Before we talk about Earth specifically, let's define what a field actually is in physics. A field is simply a region where a body experiences a force due to the presence of other bodies. For example, gravitational fields determine how objects with mass attract one another. Electric fields dictate how electrically charged objects attract or repel, and magnetic fields determine how electric currents, which contain moving charges, exert forces on other electric currents. All magnets operate on a fundamental principle. They have two poles, a north pole and a south pole. The north pole of one magnet is naturally attracted to the south pole of another. Conversely, like poles, such as two north poles, will repel each other, pushing the magnetic flux away and creating a neutral point where the magnetic forces cancel out. Earth itself acts like a giant magnet. The geomagnetic field is the magnetic field that extends from deep within Earth's interior all the way out into space. As this field reaches space, it doesn't just sit there. It actively interacts with the solar wind, which is a continuous stream of charged particles ejected by the sun. This crucial interaction is what shapes our planet's magnetosphere. So, what exactly is the magnetosphere? It is the vast region above the ionosphere, defined by how far Earth's magnetic field extends into space, stretching tens of thousands of kilometers. Think of it as our planet's primary defense mechanism. It protects Earth from the charged particles of the solar wind and high-energy cosmic rays. Without it, these harsh forces would strip away our upper atmosphere, including the vital ozone layer that shields us from harmful ultraviolet radiation. The magnetosphere is not a perfect sphere. Its overall shape is dictated entirely by the solar wind. On the side facing the sun, the relentless pressure of the solar wind compresses the magnetic field into a roughly hemispherical shape. On the opposite, night side, the field is dragged out into an enormous, elongated trail, known as the magnetotail. On a much larger scale, the sun has its own version of this, called the heliosphere, which keeps cosmic rays out of the entire solar system. The outer boundary of this protective bubble is called the magnetopause. This is the precise area where the outward pressure exerted by Earth's magnetic field perfectly balances the inward pressure of the solar wind. Because of this dynamic pressure, the magnetopause is highly asymmetric. On the sunward side, it sits about 10 Earth radii away. But on the night side, that magnetotail stretches out incredibly far, extending well beyond 200 Earth radii. Just ahead of the magnetopause, on the side facing the sun, we find a feature called the bow shock. Imagine a ship moving rapidly through water. A wave forms at the front of the bow. Similarly, the bow shock is the area where the supersonic solar wind abruptly slows down and heats up as it approaches the obstacle of Earth's magnetopause. Between the sudden deceleration at the bow shock and the final boundary of the magnetosphere lies the magnetosheath. This is a highly turbulent, chaotic region. The solar wind particles here have been slowed down and deflected, creating a swirling, unstable magnetic environment before they flow around the planet. Moving deeper inside the magnetosphere, much closer to home, we find the plasmasphere. This is a region that contains a dense population of low-energy charged particles. Unlike the outer regions that are heavily shaped by the solar wind, the plasmasphere actually rotates along with the Earth. It begins at an altitude of about 60 kilometers, encompassing the ionosphere, and extends outward to about 3 or 4 Earth radii. One of the most beautiful visual manifestations of our magnetic field at work is the aurora. An aurora is a luminous glow in Earth's upper atmosphere, produced when charged particles from the solar wind descend from the magnetosphere. Interestingly, as these particles interact with our field, positive ions slowly drift westward, and negative ions drift eastward. This creates what is known as a ring current, which actually slightly reduces the strength of the magnetic field at the Earth's surface. But how exactly does this create light? When some of these charged particles manage to penetrate the ionosphere, they collide violently with oxygen and nitrogen atoms. These collisions excite the molecular electrons, bumping them into a higher energy state. As the molecules settle back to their original state, they release that extra energy by emitting photons of light, creating the glowing auroras. Because these charged particles are forced to follow the magnetic field lines, which funnel into the atmosphere near the magnetic goals, auroras are predominantly seen at high latitudes. The magnetosphere isn't static. It constantly changes by space weather, which is driven by solar activity. When the solar wind is weak, the magnetosphere expands. When strong, it compresses. During periods of intense solar activity, the sun can erupt with a coronal mass ejection, sending a massive shockwave through the solar system. This shockwave takes about 2 days to reach Earth, triggering a geomagnetic storm. During such a storm, we see a rapid drop in Earth's magnetic field strength at the surface, and that equatorial ring current we mentioned earlier becomes massively amplified. These geomagnetic storms have profound real-world consequences. The influx of energy heats and distorts the ionosphere, which severely disrupts long-range radio communications that rely on bouncing signals off this atmospheric layer. The heated atmosphere also expands outward, increasing drag on low Earth orbit satellites and making their orbits difficult to control. Furthermore, these storms can scramble GPS signals, expose astronauts to dangerous levels of radiation, and induce massive voltage surges in electrical power grids, potentially causing widespread blackouts. Zooming out to a planetary scale, a well-developed magnetic field is crucial for holding onto an atmosphere. Planets like Earth, Jupiter, and Saturn have strong magnetospheres that deflect solar wind particles, forcing them to travel around the planet rather than bombarding the surface. Planets with weak or non-existent magnetic fields generally suffer from atmospheric stripping, where the solar wind literally blows the atmosphere away into space. There is a strange exception, however: Venus. Despite having almost no geomagnetic field, Venus maintains an atmosphere 100 times denser than Earth's, a planetary anomaly scientists are still studying. Within our magnetosphere, there are specific zones known as the Van Allen radiation belts. These are concentric, tire-shaped regions of highly energetic charged particles, mostly originating from the solar wind, that have been captured and trapped by Earth's magnetic field. The inner belt sits about 1 to 2 Earth radii away, while the outer belt is located at 4 to 7 Earth radii. By trapping these intense solar wind particles, the Van Allen belts act as an additional layer of defense, deflecting energetic radiation and further protecting our atmosphere. While these belts protect the Earth below, they pose a significant hazard to human technology in space. The intense radiation trapped in the Van Allen belts endangers satellites, meaning any spacecraft spending significant time near these zones must have their sensitive electronic components heavily shielded. As we send spacecraft beyond low Earth orbit, they must pass directly through this intense radiation zone. And as we will see as we look further out into the solar system, once spacecraft travel beyond the protection of these belts, they face even more severe hazards from unfiltered cosmic rays and solar particle events. Let's look at the magnetic fields of other objects in our solar system, starting with the Moon and Mercury. The Moon has a very weak magnetic field and lacks a magnetic dipole. Because it is so weak, it cannot prevent the solar wind from stripping away any potential atmosphere. In fact, the solar wind hits the Moon's surface directly. Mercury, on the other hand, does have a magnetic dipole, but it is incredibly weak, just about 1.1% the strength of Earth's magnetic field. Combined with its extreme proximity to the Sun, this weak field makes it nearly impossible for Mercury to sustain an atmosphere. Moving further out, Mars does not possess an intrinsic global magnetic field. Instead, the solar wind interacts directly with the Martian atmosphere, which creates a very weak induced magnetosphere. This lack of a significant protective magnetic shield is thought to be a primary reason why Mars has such a thin atmosphere today. Venus is quite an interesting case. It completely lacks a magnetic field. However, its ionosphere acts as a barrier, separating the atmosphere from outer space and the solar wind. Despite having no magnetic field, Venus manages to hold on to one of the densest atmospheres of all the terrestrial planets. When we look at the giant planets, the scale changes dramatically. Jupiter boasts the largest magnetic field in the entire solar system, which creates a massive bubble that directs the solar wind to stream around the planet, protecting its incredibly thick atmosphere. Saturn follows closely behind, possessing the second largest magnetosphere of any planet. The ice giants, Uranus and Neptune, also have significant magnetic fields that are quite similar to each other in strength and structure. Now, how exactly does a planet like Earth generate its magnetic field? This is explained by the dynamo theory. The dynamo theory proposes a mechanism by which a celestial body, whether it's a planet like Earth or even a star, generates a magnetic field and sustains it over astronomical timescales. We're talking millions of years. The core idea is that convection within the planet's liquid outer core, combined with the Coriolis effect caused by the planet's rotation, gives rise to a self-sustaining magnetic field, which we call a geodynamo. Let's break down the mechanism of this geodynamo. Inside the Earth, the temperature of the liquid outer core is extreme, ranging from about 4,400 degrees Celsius in the outer regions to 6,000 degrees Celsius near the solid inner core. These massive differences in temperature, along with variations in pressure and composition, cause convection currents within the molten iron. Just like boiling water, the cooler, denser matter sinks toward the center, while the warmer, less dense matter rises outward. This constant movement of molten iron is where the magic happens. The convection currents, the flow of this liquid iron, generate electric currents. According to the laws of physics, electric currents produce magnetic fields. As charged metals continue to pass through these newly created magnetic fields, they generate even more electric currents of their own, creating a continuous, self-sustaining loop. Furthermore, the spiral movement of these charged particles, which is caused by the Coriolis force from Earth's rotation, ensures that these separate, smaller magnetic fields roughly align in the same direction. Their combined effect adds up to produce the one vast, powerful magnetic field that surrounds our planet. Let's define what we mean by magnetic poles. The North Magnetic Pole is the specific point on Earth's surface where the geomagnetic field lines are directed vertically downwards into the planet. Conversely, the South Magnetic Pole is the point where the field lines are directed vertically upwards, emerging from the planet. If you had a compass needle that could rotate in 3 dimensions, it would point straight down at the North Magnetic Pole and straight up at the South Magnetic Pole. Because of this vertical orientation of the field lines, these points are also known as magnetic dipoles. It is important to note that Earth's magnetic field is not perfectly symmetrical. Because of this uneven distribution, the North and South magnetic poles are not antipodal. Antipodal means situated on the exact opposite side of the Earth, where a line drawn between the 2 points would pass perfectly through the center, like the geographic poles on the rotational axis. The magnetic poles don't line up perfectly like that. However, they are usually located close enough to the geographic poles that a standard compass remains a highly reliable tool for navigation. Here's a fascinating quirk about how we name magnetic poles. The north and south poles of a standard magnet are defined based on Earth's magnetic field. A magnet's north pole is defined as the end that is attracted to Earth's north magnetic pole. But remember the fundamental rule of magnetism: opposite poles attract. This means that the location we call the Earth's north magnetic pole is actually the south pole of Earth's internal magnetic field. It is the place where the magnetic field is directed downward, pulling the north end of a compass needle towards it. To simplify the complex reality of Earth's magnetic field, scientists often use an approximation called the geomagnetic dipole. Imagine a perfectly straight bar magnet placed exactly at the center of the Earth. The geomagnetic poles are the points where the axis of this hypothetical bar magnet intersects the Earth's surface. Currently, this idealized geomagnetic dipole is tilted at an angle of about 11 degrees relative to Earth's actual rotational axis. Just like with the actual magnetic poles, the North Geomagnetic Pole represents the south pole of Earth's internal magnetic field, and vice versa. Now, you might wonder why there is a difference between the magnetic poles, where a compass needle actually points straight down, and the geomagnetic poles, which are based on that hypothetical bar magnet. This difference exists because Earth's actual magnetic field is not a perfect, simple dipole. It has an uneven and highly complex distribution caused by the chaotic flow of liquid iron in the core. Over long periods, the Earth undergoes what is known as a geomagnetic reversal. This is a dramatic event where the Earth's magnetic field changes so much that the positions of magnetic north and magnetic south completely interchange. It is crucial not to confuse these magnetic poles with the geographic poles, which stay put. During a reversal, the Earth's magnetic dipole flips, causing the planet to alternate between periods of what we call normal polarity and reverse polarity. How do we know these reversals happen? The evidence comes from paleomagnetism, which is the study of the magnetic alignment preserved in rocks at the time they formed. By studying these rocks, scientists have observed that over the last 20 million years, the magnetic north and south have flipped roughly every 200,000 to 300,000 years. However, unlike the Sun, which reverses its field every 11 years like clockwork, Earth's reversals are not periodic. The time between flips can be as short as 10,000 years or as long as 25 million years. And the actual process of reversing takes a few hundred to a few thousand years, during which magnetic poles can emerge at odd latitudes. To clarify the terminology, let's define the polarities. In normal polarity, which is the state we are currently in, Earth's north magnetic pole, which remember is the south pole of the internal magnetic field, lies relatively close to the geographic north pole, also known as true north. In reverse polarity, the entire system is flipped. Earth's north magnetic pole would be located close to the geographic south pole, or true south. Even during periods of stable polarity, the magnetic poles do not sit still. They constantly wander due to the dynamic changes in Earth's magnetic field, a concept known as polar shift theory. Currently, the North Magnetic Pole is located north of Ellesmere Island in northern Canada, but it is rapidly drifting towards Siberia. Historically migrating at about 10 kilometers per year, its speed has recently accelerated to about 40 kilometers per year. Meanwhile, the South Magnetic Pole is currently located off the coast of Antarctica, actually sitting outside the Antarctic Circle. So how does all this affect a simple compass? A compass needle is a tiny magnet, and it points towards the magnetic north because the Earth itself acts like a giant magnet. The south pole of Earth's internal magnetic field is located near the geographic north, attracting the north end of the compass needle. Because Earth's magnetic dipole field is aligned fairly closely with the Earth's rotational axis, a compass is incredibly useful for navigation. It doesn't point exactly to true north, but the wandering of the pole is slow enough that a compass remains a reliable tool. Humans aren't the only ones who rely on Earth's magnetic field for navigation. Through a biological phenomenon called magnetoreception, various organisms can actually sense the magnetic field and use it to orient themselves. This incredible ability is found in a wide range of life forms, from certain types of microscopic bacteria to massive sea turtles, and is famously used by migratory birds and homing pigeons to travel thousands of miles across the globe with pinpoint accuracy. Because the magnetic poles and geographic poles don't perfectly align, navigators must account for magnetic declination. Magnetic declination is simply the angle between magnetic north, where your compass points, and true north, the geographic pole. If the compass points east of true north, the declination is considered positive. If it points west, it is negative. Understanding and correcting for this angle is absolutely crucial for ships, aircraft, and any long-distance transport to ensure they stay on the correct course. While we are discussing compass errors, it's important to distinguish declination from magnetic deviation. While declination is caused by the Earth's global magnetic field alignment, magnetic deviation is a localized error. It is the deflection of a compass needle caused by the magnetic influence of nearby metallic objects, such as the steel hull of a ship, electronic equipment, or even a metal watch on your wrist. Both must be accounted for, but they have very different causes. Another important concept is magnetic inclination, also known as magnetic dip or dip angle. This is the angle that Earth's magnetic field lines make with the horizontal surface of the Earth. In simple terms, if you held a compass vertically, it's the angle the needle would point downward or upward. This is particularly important in aviation because magnetic dip can cause an airplane's compass to give erroneous readings during banked turns and changes in airspeed, requiring pilots to make necessary corrections. The angle of magnetic inclination changes depending on where you are on Earth. At the magnetic poles, the dip is a full 90 degrees. The needle points straight down. But at the magnetic equator, the dip is 0 degrees. The magnetic field lines are perfectly parallel to the ground. The magnetic equator is an irregular, imaginary line that passes around the Earth near the geographic equator. And just like the magnetic poles, the magnetic equator is not a fixed line. It constantly shifts and changes shape as the Earth's internal magnetic field evolves. Let's apply what we've learned to a real-world examination question from the UPSC prelims in 2005. The question asks you to consider 3 statements. Statement 1. The axis of the Earth's magnetic field is inclined at 23.5 degrees to the geographic axis. Statement 2. The Earth's magnetic pole in the northern hemisphere is located on a peninsula in northern Canada. Statement 3. The Earth's magnetic equator passes through Thumba in South India. You are then asked to identify which of these statements are correct from the given multiple choice options. Let's break down the statements. Statement 1 is incorrect because the Earth's magnetic axis is inclined at about 11 degrees, not 23.5, which is the tilt of the rotational axis. Statement 2 is also incorrect. The North Magnetic Pole is located north of Ellesmere Island, which is an island, not a peninsula, and it is rapidly drifting. Statement 3, however, is correct. Thumba in South India is very close to the geomagnetic equator. This location features a strong equatorial electrojet current, making it the ideal site for the Thumba Equatorial Rocket Launching Station, built in the 1960s. Therefore, the correct answer is D, 3 only. To wrap up our discussion, let's review the key takeaways. We saw that magnetic fields vary wildly across the solar system, with Earth's robust field being generated by a geodynamo driven by convection in the liquid outer core. We learned that magnetic and geomagnetic poles are distinct from true geographic poles, and they are constantly wandering. Over long geological timescales, the Earth even undergoes geomagnetic reversals, completely flipping its magnetic polarity. Finally, while the magnetic field is incredibly useful for navigation via compasses and biological magnetoreception, navigators must always account for variations like magnetic declination and inclination.